up. Let's see. All right, now, I know you guys, maybe some of you guys don't like this whole process, but here's something really nifty to me. I don't know if I really want to necessarily do this, but two things I want to say about this. There's what we just did. That is an area of a rectangle, height times width. If I add them all up, I get an estimate for under the curve to the x-axis. And if I make my resolution infinite, I get the exact area. Right? So that's the steps of how we generated this. And that's why the process becomes get expressions for these, throw them in, and work with it, because the concept is true. Just figure out what goes in there and do it. Now, what's really, really cool. Do you guys remember there were two sections that dealt with the limit definition of derivative? One of them said plug in a number. So you find the slope at that number. And then the other one was better. It said, no, don't plug in numbers where shit. Get a function that represents the slope everywhere. Does everybody remember that? There was one you had to put in like 3, and you did the whole limit thing. And then if you wanted to know at 4, you'd have to do it all over again. And the next section said, oh yeah, let's just put x in there. And then we can make it whatever we want to. We don't have to do the whole process over and over and over again. Now, maybe you remember. What we just did is specific to 0 to 3. If I did that whole process over again, and I get a feeling you guys might not want to see this, but if you do want to see it, I can do it with you. If I did it from 0 to t, I'm not going to tell you what the other side is. If you do this whole process, it comes out to be the antiderivative of that. That is really flippin' cool to me. Now to prove that this process always leads to the antiderivative, you'd have to put every possible function in there and do it. Shit. But it's at least really good evidence. You're like, oh, maybe there is a connection. We saw the connection made in the last problem. Very weak. No evidence. We just did it and went, oh shit, look, it's the same number. Okay. So we need to make this connection. There has to be an easier way, dear God. In fact, I told you that one we did earlier from the book, where it was like over x, I can't remember, and you had to just put the form down. They said, don't do the limit. You cannot do that. You can't. It's just, you can't evaluate that limit, at least nowhere near easy. So this process is going to suck the minute I've got, think about natural log. How the hell would that shit work with this? No way. No way. So there must be some other way to get this area. And it looks like with some of the stuff we talked about, maybe it's a connection to the antiderivative. Maybe there's a connection there. So the way we build this connection, the next two things we're going to talk about sound very important. One is called the fundamental theorem of calculus part 1. And the next one is, of course, part 2. So what I affectionately call F-Talk 1 and F-Talk 2. Fundamental theorem of calculus. So I just want to get, we don't have the most time left, but I just want to get a little bit of a feel for what's going on here. To get into this, let me do this. Oh, this is the connection I needed to make with that. Let me rewrite this again. I want to show you a better way to write this. Get out of there. All right. I kind of teased this better way to write it. Remember the long SS we talked about? It's a sum, but it's infinite, so let's make it a long S. That was the thinking. That is the history of that. Go with me here, now watch. if I let the rectangles go to infinity, what happens to the width of each one? They approach 0, but they don't get there, do they? Because do I get to infinity? No. So we already know how to represent an infinitesimal change on the x-axis. How do I represent that? Delta x is a big step. What do I use for an infinitesimally small step? Think derivatives. Instead of delta x, I use, what do we use for derivatives? Dx. I love it. So this is going to become dx. This one, see how this is, let me see if you guys, this is what's called discrete. It's not continuous.